All right, so in this video, we're going to go over an introduction to counting. So let's go ahead and get started. Okay, so just one thing, I'm going to talk about counting not in a super formal way, but by introducing you guys to different types of problems which you're going to see. And when you see how I solve these problems, I'll introduce different techniques and why they're correct. All right, so anyway. All right, so in our first question, I have 3 shirts and 2 pants. So the question is, how many different outfits can I create? So an outfit, it consists of a shirt and it consists of a pant. So I'm going to need 1 shirt and 1 pant in my outfit. So let's say that I call my shirts S1, S2, and S3, and I call my pants P1 and P2. So I'm just keeping these subscripts to just keep in my mind which pant is which. So for example, here is one possible outfit. So I can wear the first shirt and then the second pant. This is a possible outfit. Another possible outfit is I wear the third shirt and then the first pant. And of course, I have some more possible outfits. So the question is, how many do I have in total? All right, so let's go ahead and see. So these outfits, I can kind of break them up into different scenarios. So like I could have those outfits where I'm wearing the first shirt. So for example, I wear the first shirt and I have 2 choices. I have the first pant and I have the second pant. I have those outfits where I wear the second shirt. And in this scenario, I also have 2 pants to choose from. And I have those outfits where I wear the third shirt. And in combination with this third shirt, I can choose either of the first 2 pants. So as we can see, in total, I have this outfit right here. It's like the first shirt, first pant, first shirt, second pant, second shirt, first pant, second shirt, second pant, third shirt, first pant, and third shirt, second pant. Okay, so in total I have 1, 2, 3, 4, 5, 6 outfits. So 6 is my answer for this question. So as we can see, we pretty much like multiplied 3 and 2. So this is an example of us using the multiplicative principle. If we wanted, we could have just done 3 times 2 and we would have gotten 6. All right, let's go on to the next question. We roll a die and we flip a coin. The question is, how many possible outcomes are there? So on our die, here are the possible outcomes. It's a 6-sided die. So on a 6-sided die, there are 6 different faces, so 6 different possible outcomes. And those outcomes are 1, 2, 3, 4, 5, 6. And on our coin, there are only 2 possible outcomes. There is heads or there's tails. So if we're interested in how many total possible outcomes there are, again, let's assume that the coin is a head. Then I have 6 possibilities for the dice roll. And if the coin is a tail, there are another 6 possibilities for my dice roll. So I'm writing them all out here. And we see there's 6 here and there's 6 here. So in total, there are 2 times 6, or 12 different possibilities. All right, let's go on to the next question. In how many different ways can we arrange the letters in the word cat? So we could just write them out if we really wanted to. So I could have CAT. I could swap these two around, CTA. Maybe it doesn't start with C, it starts with A. Okay, so with those other ones starting with A, I could swap C and T around, so it becomes TC. Maybe it doesn't start with C, maybe it doesn't start with A, maybe it starts with T. That's the last possibility. Okay, I have TAC. And of course, these AC can be swapped around to CA. So you can kind of see I wrote these systematically. So like there's a few cases, right? So it could start with the letter C, it could start with the letter A, or it could start with the letter T. So for each of these three cases, the other two letters have like two different orders in which they could be. So I make sure I count those two orders. So for example, I have AT here, and I swap them here, and I have TA. CT here, TC. AC here, CA. So I'm basically swapping these orders, but I am breaking this problem up into cases effectively. So for certain counting problems, when I'm counting the number of ways, let's say I'm arranging something, I can break the problem up into cases as I did in this example. So we can count, there are 1, 2, 3, 4, 5, 6 different ways to arrange this word. Okay, so now this is one way which we can solve the problem. Perfect. Let's talk about another way in which we can solve this problem. So let's imagine that I'm looking at only my first letter right here, only my first letter. So how many ways are there for me to choose what is going to be this first letter? Well, I could have C as my first letter, I could have A as my first letter, or I could have T as my first letter. So there are three different ways for me to choose what goes here. Okay, now I've placed this first letter. Let's say I put a T. All right, so now I have two different choices for what can be my second letter. So I can pick either of the two, so there's two ways. Okay, let's say I put in A. At this point, my last letter is guaranteed. So there's really only one way, and that letter is going to be C, and there's only one way. So if I want to find how many ways there are to arrange the letters, I could just multiply these three numbers by each other. And 3 times 2 times 1, it turns out to be 6. Okay, so that's another way we could do it. The number of different arrangements of three different letters, by the way, there's a special term for this. It's called a permutation. Okay, so a reordering is a permutation. We're going to talk more about permutations in future videos and through the readings, which I highly encourage you go through. They talk about permutations in detail as well. Okay, here's like another thing which is important. You see these numbers 3 times 2 times 1. Sometimes you're going to have like even bigger numbers. So for example, you might have like, okay, so for example, you might have like 5 times 4 times 3 times 2 times 1. So like you have all the numbers down to 1. So there's like a special symbol for this. You write this with a 5 with an exclamation point. In general, you write n times n minus 1 times n minus 2 all the way until 1 as n factorial. You read this as factorial. This exclamation point reads as factorial. All right, let's move on to the next problem. Alice, Bob, Charlie, and Diana are in a race. Assuming there are no ties, how many different rankings are possible at the end of the race? So clearly there's a first place, second place, third place, and a fourth place. So here's one possibility. So Alice comes first, then Charlie, then Diana, then Bob. Okay, that's great. Here's another possibility. Charlie comes first, Bob comes second, Alice comes third, and Diana comes last. So these are two different possibilities, right? So we got to figure out how many possibilities are there. So the number of possibilities is the number of reorderings. That's something that's important to keep in mind. And if you do remember from the last question, maybe you could guess what the problem is, but if not, that's okay. Let's go through this with a similar technique. Okay, so in the first position, we're gonna pick first place, right? Who goes in first place? And there's 4 people who can be in first place. So based on that, there are 4 possibilities here. There are 3 people which can be in second place. Based on that information, there are 3 possibilities here. Why are there 3 people? The first person is chosen, and then there are 3 other people after that. Okay, so the first 2 people, we already know where they rank in the race, or like who those first 2 people are in the race. So now we can see that for the third person, third rank, there are only 2 people to choose from. And finally, there's only 1 person. So the number of different ways is 4 times 3 times 2 times 1, which is 4 factorial. That's like the symbol for it. But if you actually multiply those out, you get 24. All right, next question. All right, a license plate consists of 3 letters and 3 numbers. How many different possible license plates are there? Okay, so let's just assume that the letters are in the beginning and then the numbers are at the end. Or maybe the numbers are at the beginning, the letters are at the end. Okay, so I have number 1, number 2, number 3, and I have letter 1, letter 2, letter 3. Okay, so by number, I mean digits, right? So I mean digits from 0 through 9. So it turns out that this is just 10 digits. And how many letters do I have to choose from? Well, I have the letters from A to Z, and that is 26 letters. Okay, so right here, I have 10 possibilities for whatever digit I have here. Okay, so now I have 10 possibilities. So here's an incorrect answer. Okay, so I have 10 digits here, and now I have 9 digits here. So why is this incorrect? Well, this is incorrect because we're trying to follow the same strategy as the last time. Like, okay, if the second digit can't match with the first digit, okay, then there's 9 different choices remaining. But in reality, the second digit can still be anything from 0 through 9, right? So there's still 10 choices, right? So this can be from 0 to 9, this can be from 0 to 9, and this one can be from 0 to 9 too. So there's 10 choices here as well. Okay, now for our letters. The first letter, it can be anything from A to Z. So there's 26 possibilities. Same for the second letter. There's 26 possibilities, and same for the third letter. There's 26 possibilities. So the number of different ways I can form a license plate is 10 times 10 times 10 times 26 times 26 times 26, which is equal to 26 to the power of 3 times 10 to the power of 3. And I'm not going to calculate that, but if you have a calculator, feel free. It's going to be a relatively large number. Maybe if I had to guess, like, I don't know, like 8 million, 10 million, something. More than 10 million, it's just a guess. All right, so how many ways can we arrange the letters in the word math? All right, so again, this is like, I think it's just the same question as before, right? Like, it seems like the same question. So for this first answer choice, for this first first letter, we have 4 choices. Let's say we chose like A. Now we have 3 other letters. Let's say we chose like T. We have 3 other letters. Okay, now we have 2 other letters. Let's say we chose M, and then our last letter, it has to be H at this point. So we could just multiply these out, and this is going to equal 24. All right, now how many ways can we arrange the letters in the word bubble? Okay, this time we have 6 different places here. So I'll show you a mistake. So a mistake is, okay, so it's just like 6, 5, 4, 3, 2, 1. So this is like 6 factorial, and this is equal to 720. So this is a mistake. And I'll show you why this is a mistake. So this assumes that, like, okay, if I choose the letter B, for example, then like the second time I have to choose a different letter. But in reality, this is not what actually happens. Like, for example, if I choose a B as my first letter, the second letter can still be a B, which is a little bit confusing, right? So here's what we could kind of consider. So like all these, like the complication here occurs from the fact that I have multiple letter B's. So there, like, maybe if I just like write a label for each of these letter B's, that will like help out a bit. Okay, so this is B1, B2, B3, and then the other 2 letters. So for example, these 2 permutations are actually equivalent. These 2 reorderings or permutations are actually equivalent to each other. So this is going to be equivalent to this. And as you can see, like the order of the B's is swapped, but the actual like arrangement is really the same, because the B's are actually the same, even though we're treating them as different above here. So we can kind of see that, like, for any arrangement, there's a particular orientation of these letter B's. So in the calculation above, it's sensitive to this orientation, but in like any actual arrangement, like I don't care what the like ordering of these B's are. So the question becomes, how many ways are there to order the B's? Well, they could be in this order as here. They could be like B1, B2, B3. They could be in this order here. They could be like B1, B3, B2. They could be like B2, B1, B3, B2, B3, B1, B3, B1, B2, and B3, B2, B1. So we could have these like different ordering. We could have these 6 different orderings effectively. So what this means is that for every one of these 720 arrangements, there's actually like for every one of those arrangements, there's actually like 5 other equivalent ones to it. There's 5 other equivalent ones to it. So in order to correct for this, I have to actually divide my answer by 6. And when I divide my answer by 6, I get my actual answer of 120. So the number of ways to arrange the letters in the word bubble is 120. All right, this next question, how many ways can we arrange the letters in the word bubble such that the arrangement starts with a vowel? Okay, so for example, this is one way. All right, so this problem is a little bit different. Let's first start by identifying what the vowels are. So B is not a vowel, U is a vowel, L is not a vowel, E is a vowel. So it has to look like U followed by something. That's one case. Or it could look like E followed by something. That's another case. So these two cases can't occur at the same time. If they could occur at the same time, then we'd have to do a correction afterwards, but they don't occur at the same time. But for those arrangements which start with a U, with the letter U, we have to somehow permute, we have to somehow reorder these other letters. Maybe I missed one. Okay. B, 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 L, E. So I have to reorder these 5 letters. For those arrangements which start with an E, I have B, 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 U, L, which I have to rearrange. So the question becomes, how many rearrangements are there in this case? How many rearrangements are there in this case? And I have to add those two answers. So luckily for us, these cases are actually like the same. I know there's like an E instead of a U here, but like the calculation will be the same. So let's just calculate it for one of them. And for the bottom one, we know the answer will be the same. So we have 5 different letters, which we have to rearrange. So we have 5 times 4 times 3 times 2 times 1. But we do have to make a correction because the actual ordering of these B's doesn't matter. So we have to divide by the 6 orderings for these B's. And by the way, it turns out that there are 3 factorial or 6 orderings of these B's. So that's something to keep in mind. And as you solve more problems and as you read the lecture notes, you will understand this concept more in detail. Okay, so the number of orderings is 5 times 4 times 3 times 2 times 1 divided by 6. And it turns out that this is equal to 20. So in this case, there are 20 orderings. In this case, there will also be 20 orderings. So these are the 2 cases for our problem. We're just breaking it up. And that means in total, our answer is 20 plus 20, or 40. All right, fantastic. So this is going to be, there are more problems, but I think this is a good ending point for the video right here. There are a lot of concepts to digest for now. I'm going to be making another video on this topic very, very soon, and we're going to be going far deeper into these concepts, but I think this is a great starting point. All right, so I will see you in the next video.